This is a climactic moment. Right now, 4 humans are heading to the moon. For the first time in 54 years, they ride atop the most powerful rocket NASA has ever built, a multi-billion-dollar marvel of technology. But this victory conceals a deadly paradox. The most expensive mission in human history could fail because of a 50-year-old technology. Because the heat shield protecting the Orion capsule shattered on its first test flight, the exact same material used on Apollo. This time tore away from more than 100 different locations. This was not supposed to happen. Engineers discovered that gases built up inside the shield in the 2,700 degrees Celsius inferno, causing it to blow apart. Because of this, the astronauts will be forced into a steeper descent. But the truly shocking part is that this solution is just a guess. If a mind-bending gamble on a multi-billion-dollar mission excites you, then join the channel. Because the real story behind why this shield cracked will change everything you thought you knew. Let's begin. Right now, as you listen to this, 4 people are farther from Earth than anyone has been in over half a century. Their names are Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen. They are sealed inside a capsule named Orion, in a spacecraft they themselves named Integrity. They are soaring through the void between Earth and the Moon at thousands of kilometers per hour. But this journey itself is only part of the real story, because the story of humanity's return to the Moon is a far more complex and far more human tale than a single rocket launch. This story is a case study in how a species that once achieved the impossible could fail for decades to repeat that same achievement. This is the paradox that should disturb you. In 1969, we sent humans to the moon with computers that had less processing power than the device you're listening to this on. The Apollo Command Module's guidance computer had about 74 kilobytes of memory. It ran at a clock speed of about 2 megahertz. A modern smartphone is millions of times more powerful. So, it's astonishing to look at what was accomplished with the technology of the day. The Saturn V rocket that carried them there was designed using slide rules and hand-drawn engineering diagrams. The heat shield was tested with technology that would be considered primitive by today's standards. The communication system that connected mission control to the astronauts 400,000 kilometers away operated on a bandwidth thinner than a modern home internet connection. But they still succeeded 6 times. 12 people stood on the surface of another world. They looked back at the Earth, and they returned safely. We had less technology, we had less computing power, we had less materials, science, less simulation capability, less understanding of space radiation. We had less of everything, except for one thing: will. Now, we have exponentially more resources, more knowledge, more infrastructure, and more experience. And yet, it has taken us 54 years just to send 4 people on a trip around the moon. Not a landing, but just a loop and a return. The most powerful space agency on the planet, backed by the largest economy in human history, needed more than half a century to repeat the opening act of a mission that had become routine by 1971. One of the most jarring truths at the heart of this situation is institutional amnesia, because the blueprints for the Saturn V still exist, but the manufacturing ecosystem that built it is gone. The factories are closed, the suppliers have vanished, The engineers who understood the tolerances, the materials, the subtleties of construction that never made it into the official drawings, have retired or passed away. This is why the problem is so deep. Because knowledge in engineering is not just what is written down. It is something that lives in the hands and minds of the people who do the work. And when those people are gone, yes, the knowledge goes with them. Every cancellation disbanded engineering teams. Every new program started partially from scratch, reinventing solutions to problems that had been solved, and then forgotten, decades earlier. A condition called skill atrophy set in. Muscle memory is lost, instinctive reactions dull. That subtle, undocumented knowledge held in the hands and intuition of experienced technicians, the feel for a seal that isn't quite right, the recognition of a pressure curve that looks slightly off, erodes with disuse. But perhaps even that wasn't the real problem. The real problem was the loss of the driving force. The Apollo program existed for one reason and one reason only: the Cold War. The Soviet Union had launched the first satellite, the first animal in orbit, the first man in space, the first spacewalk. Every milestone belonged to Moscow. The United States was losing a geopolitical race that the entire world was watching. And the moon became the finish line. So, President Kennedy didn't propose the Apollo program because he was passionate about lunar geology. He proposed it because the nation's prestige was on the line. Money flowed, risk was accepted. Decisions were made at a speed that would be unimaginable in today's corporate environment. 8 years passed between Kennedy's speech in 1961 and Armstrong's footprint in 1969. Just 8 years, from political commitment to humans standing on another world. The Artemis program, however, had no equivalent driving force, or rather, it didn't until recently. See budget cycles, changing administrations, shifting priorities. Each one eroded the program's momentum. The timeline slipped. 2024 became 2025. 2025 became 2026. This is why the technological paradox, the lost knowledge, and the missing will all combined to create a half-century pause. But this story assumes we are only trying to repeat the past. In truth, that is not the case, because the Artemis program represents a fundamentally different philosophy than Apollo. This mission isn't designed just to visit the moon. This is designed to live there, to build infrastructure, to extract resources. And that includes something at the moon's south pole that Apollo never looked for. Something that changes the entire equation of deep space exploration, because this new vision is built on the most valuable treasure beneath the moon's surface: water. But not water as we know it. Water ice, frozen for billions of years in craters that have never seen sunlight. And this discovery transforms the moon from a mere destination into a gateway to the entire solar system. How is this possible? The answer lies in the moon's axis, which has almost no tilt. Earth's axis is tilted 23.4 degrees. This is why we have seasons. But the moon's axis is tilted just 1.5 degrees. It stands almost perfectly upright. The result of this is that mountains and crater rims at the poles create permanent shadows that stretch for kilometers. Since the moon has no atmosphere, there is nothing to scatter the light. So the shadows are absolute. In the depths of these craters, sunlight has not reached the soil in billions of years, perhaps since the craters themselves were formed. These are permanently shadowed regions, and they are the coldest known places in the solar system. Temperatures drop to around -240 degrees Celsius. That is colder than the surface of Pluto. It is even colder than the nitrogen ice plains of Triton, Neptune's largest moon. At these temperatures, water molecules that would instantly vaporize in sunlight are trapped. They freeze solid, and they remain frozen indefinitely. The moon is not the dry, dead rock we once assumed. It is a giant freezer, and that freezer has been running for 4 billion years. But what makes this water ice so important is not just its existence, because water isn't rare in the solar system. It's on Europa, it's on Enceladus, it's on Mars. But the water on the moon is just 3 days away by spacecraft. It's accessible, and it can be converted into the two most critical commodities for space exploration: breathable oxygen and rocket fuel. This concept is called in situ resource utilization, and it is the difference between exploration and colonization. Water is 2 hydrogen atoms bonded to 1 oxygen atom. Electrolysis, the process of passing an electric current through water to split it into its component gases, is a technology known since the 18th century. If astronauts can extract water ice from the lunar regolith and electrolyze it, they can produce oxygen to breathe and hydrogen to burn as fuel. The moon becomes a refueling station. This is why the Artemis program is completely different from Apollo. Every Apollo mission carried everything it needed from Earth. Every gram of food, every liter of water, every molecule of oxygen, every drop of fuel was launched from our planet's surface at enormous cost. A single space launch system, or SLS rocket launch, costs approximately $4.2 billion. If every mission to the moon requires launching every consumable from Earth, the program becomes economically unsustainable. But if astronauts can produce oxygen and fuel from local resources, the cost per mission drops dramatically. The logistics chain shortens. The mission duration extends. What was once a 3-day camping trip becomes a settlement. This means humanity can break its dependence on Earth. And all of this leads us to a much bigger goal. Because Artemis is not just about going back to the moon. It is a test of whether humanity can become a multi-planetary species. Not in theory, not in science fiction, but in engineering reality. The moon is the exam. Mars is the real mission. If we can't do this on the moon, a 3-day trip by spacecraft, we certainly can't do it on Mars, which is at least 7 months away. The technology required to survive at the lunar South Pole is the same technology required to survive on Mars, just scaled up and improved. So, these plans were made not just to repeat a past achievement, but to secure our future. But plans are one thing. Theories on paper take on a whole new form when they collide with the unforgiving reality of space, because the first sign that returning to the moon would not be so simple emerged not during a failure, but in the aftermath of a mission celebrated as a massive success. And right then, in the midst of victory, the first shocking truth emerged. The Artemis 1 mission had launched on November 16th, 2022, after 2 postponed attempts due to hydrogen leaks and a tropical storm. This was an uncrewed mission, a test flight. It was designed to prove that the Space Launch System rocket and the Orion capsule could withstand the journey to the moon and back. The mission lasted 25 days and 10 hours. Orion reached a distance of about 432,000 kilometers from Earth. farther than any spacecraft designed to carry humans had ever gone. NASA declared it a triumph, and it truly was, until engineers looked at the heat shield. The heat shield, it was in pieces. When Orion plunged into Earth's atmosphere at nearly 40,000 kilometers per hour, the friction between the capsule and the atmospheric gases generated temperatures exceeding 2,700 degrees Celsius on the heat shield's outer surface. This was normal. This was expected. But when engineers inspected the shield post-landing, they found something deeply disturbing. The coating, called avcoat, hadn't ablated uniformly. It had cracked. It had fractured. It had broken off in chunks. There was unexpected material loss at over 100 locations on the shield. This pattern of damage had never been observed during the Apollo missions, even though the same material was used under similar conditions. This was not supposed to happen. The investigation took months. The conclusion was this: gases produced by the extreme heating were becoming trapped inside the avcoat material. Normally, these gases were supposed to vent away. But the specific formulation used on Orion wasn't permeable enough. The gases had nowhere to go. Internal pressure built up within the material. It eventually exceeded the structural strength of the coating. The shield had cracked hogshead from the inside out. On an uncrewed mission, this is just a data point. But on a crewed mission, this could have been a death sentence, because the heat shield is the only barrier between 4 human beings and temperatures that would vaporize them in milliseconds. There is no backup system. There is no second shield. But the heat shield was only the first problem. It was not the last. On January 17th, 2026, the fully assembled Space Launch System rocket, with the Orion spacecraft mounted on top, was rolled out to Launch Pad 39B at the Kennedy Space Center. The 98-meter-tall structure was an engineering cathedral pointed at the sky. But what followed was not flawless. During the first full fueling test, engineers detected a leak in the liquid hydrogen system. The rocket stages were supposed to be loaded with about 2.6 million liters of liquid hydrogen and liquid oxygen. Hydrogen is the smallest molecule in the universe. At the negative 252 degrees Celsius required for rocket propellant, just above absolute zero, it becomes a liquid so cold that it shrinks every gasket, every seal, every fitting it touches. Keeping liquid hydrogen contained is one of the toughest challenges in rocket engineering. Leaks are not uncommon. But they are also not acceptable because hydrogen is explosive. The seals were replaced. The test was rescheduled. And the second test was a success. The rocket was signed off as ready for flight. But the relief was short-lived. During a routine post-test procedure, engineers discovered another anomaly. The helium was not flowing properly. The pressurization system was underperforming. Helium is used to prevent the tanks from collapsing as fuel is consumed and to purge the engine lines before ignition. Without proper helium flow, the upper stage cannot function. Without the upper stage, Orion cannot get to the moon. And this is where the problem turned into a logistical nightmare, because the faulty part was buried deep within the rocket, as it was in a section that was physically inaccessible while the vehicle was standing upright on the launch pad. The tight integration made it impossible to repair. NASA had no choice. They had to roll the entire 98-meter stack, the thousands of tons of rocket, spacecraft, and support structure, all the way back to the vehicle assembly building, the giant hangar where the rocket was first assembled. Weeks were lost from the schedule. These failures, the hydrogen leak, the helium valve, the heat shield cracking, are not isolated incidents. They are symptoms of a deeper structural problem. What NASA Administrator Jared Isaacman publicly called skill atrophy. The workforce that builds, tests, fuels, science, and launches this rocket is only practicing the entire process once every 3 to 4 years. Muscle memory is fading. Instinctive reactions are dulling. 4 people are entrusting their lives to SEALs that have failed before. A heat shield that has cracked before. A rocket that has only flown once. And a workforce that even its own administrator admits is out of practice. But beyond all these technical and human risks, there was one more risk that NASA took to get this program off the ground. A risk they have carefully avoided talking about loudly in public. The probability of a loss of crew, and the fact that this probability, because that probability itself, reveals the greatest chasm between the Apollo era and today. In the Apollo age, the tolerance for risk was extraordinary by modern standards. The astronauts knew they were flying experimental vehicles into an environment that had already killed people. Apollo 1 had killed 3 astronauts in a ground test. Apollo 13 had nearly killed 3 more. But that's not the real shock. The real shock is in the numbers. It was estimated that the probability of a catastrophic failure on any given Apollo mission was roughly between 5 and 10%. 1 in 20, 1 in 10. The astronauts accepted those odds because the mission was considered worth the risk. The nation accepted them because the geopolitical stakes were existential. But today, that tolerance is different. Society has changed. Media scrutiny is absolute. A single loss of crew on Artemis could end the entire program. Not delay it, end it. The political will to continue after the death of 4 astronauts on live television is far more fragile in the age of live streaming and instant analysis than it was in 1967. This is why NASA officials, when pressed in public hearings to state the probability of mission failure for Artemis 2, have carefully avoided giving a specific number. That silence speaks volumes. They know the risk is not zero. They know it is not negligible. And they know that admitting it too precisely would create a public relations crisis that could ground the program before it ever proves itself. But the most staggering blow was yet to come, and it targeted the emotional anchor of the entire program. For years, Artemis 3 was a promise. It was the mission that was supposed to close the circle. The mission where boots would finally touch the lunar regolith for the first time since 1972. Every press conference, every congressional hearing, every NASA animation showing astronauts bouncing on the lunar South Pole pointed to Artemis 3 as the Great Return. The moment the 54-year absence would end. The moment humanity would prove it could still do the hardest thing it had ever done. In February 2026, NASA shelved that plan. Artemis 3 would not land on the moon. This was not supposed to happen. This went against every promise made. The mission was redefined as a 30-day all-systems test in low Earth orbit. The crew would launch on Orion Hardship Rendezvous and dock with either SpaceX's Starship Human Landing System or Blue Origin's Blue Moon lander. But that's all. Everything would be tested in the relative safety of Earth orbit. No one was going to the moon on Artemis 3. The first actual landing target was pushed to Artemis 4 in early 2028. The goalposts had moved again. They had moved so many times that tracking their trajectory required a spreadsheet. The original target for a moon landing was 2024. Then it became 2025. Then 2026. Now 2028. 11 years after the program was announced. That was longer than the entire Apollo program. From Kennedy's speech to the final landing. But this frustrating decision was not made irresponsibly, because the previous plan demanded a miracle. It was more of a gamble than an engineering plan, and an independent safety panel had issued a warning that this gamble was unacceptable. When you stack multiple independent risks together in a single mission, the probabilities don't add, they multiply. The chance of everything going right plummets. The panel's conclusion was that attempting all of these firsts simultaneously on a mission to the lunar surface with crew on board was not prudent engineering. It was an invitation to disaster. NASA listened, and it chose caution over spectacle. So what was it that made the original plan so dangerous, so close to impossible? Because what Artemis 3 was supposed to achieve in a single mission was not a simple repeat of Apollo. It was a massive architecture that required a series of impossible feats, never tried before, to work perfectly, all at once. And at the center of this architecture, because at the center of this architecture lay a radical model, completely different from Apollo. It was far more than one landing, one ascent, march, and one return. It was a massive plan that required a series of complex and risky maneuvers. A ballet performed in orbit at TS to work flawlessly, a sequence never attempted before. To truly understand the reason for the shocking delays and plan changes in the previous section, we must now slow our pace and descend into the technical details of this architecture, because the devil was in the details, and these details reveal just how unforgiving human spaceflight can be. The first and most fundamental difference was the change in philosophy in the mission's architecture. The Apollo program was like a single package. Just like when you go on vacation, you put everything you need into one suitcase and set off. The Saturn V rocket carried the command module and the lunar module at the same time. In a single launch, everything left Earth together and went to the moon together. The crew separated the lunar module in lunar orbit, descended to the surface, then returned to the command module and flew home in one piece. All this hardware was designed, built, and tested by a single agency, NASA, within a single ecosystem of prime contractors. The parts were born to talk to each other. But the original plan for Artemis 3 was completely different from this integrated approach. It was like a Lego set assembled in orbit. The Orion capsule was launched by the Space Launch System, or SLS. This was only the first piece of the puzzle. The landing vehicle, SpaceX's Starship, was to be placed in orbit by a completely separate launch. And this meant that two vehicles, Shakti, designed by two different organizations, two different engineering philosophies, and two different control systems, had to come together in the vacuum of space before the mission. In Apollo, all the hardware were members of a single family. In Artemis, Kajtahazi N, two strangers had to meet for the first time, hundreds of thousands of kilometers away. This added a fundamental complexity and multiple points of failure to the mission's nature. Because the success of a single launch was no longer enough, multiple Hakki independent systems had to work perfectly. But the real impossibility lay in the second technical mechanism, orbital refueling. Starship is the largest spacecraft ever built, and this massive size caused it to collapse under its own weight. Think of it this way. The amount of fuel required for Starship to land on the Moon and return is so immense that it cannot be launched from Earth with a full tank. Just as a cargo plane cannot take off with both its cargo and all its journey fuel at the same time, the fuel mass exceeded the rocket's capacity to carry it into orbit. So, the solution was something never attempted on this scale before: refueling in orbit. According to the plan, some estimates suggested that between 10 and 16 Starship tanker flights would be required. These tankers would carry the fuel to orbit and transfer it to the waiting lunar lander version of Starship. This transfer involved pumping hundreds of tons of cryogenic, or supercooled HUS, fuel between vehicles in microgravity. In the vacuum of space, at temperatures near absolute zero, these fuels, namely liquid methane and liquid oxygen, are like constantly boiling liquids. If they are not kept cold enough, they will vaporize and be lost. This meant the entire refueling process had to be completed flawlessly within a specific time window. If any tanker launch failed or was delayed, the fuel in orbit would start to boil off, potentially requiring the entire sequence to be restarted. Apollo had no such problem. Because the lunar module was small and could carry its own fuel, Starship, however, was a giant. And quenching this giant's thirst required setting up a network of gas stations in orbit. And that gas station had never been built before. The third technical hurdle was the rendezvous of these two foreign vehicles, docking and crew transfer. The original Artemis 3 mission required the first crewed docking between Orion and Starship. This was not a simple merger. It meant that systems produced by two different companies, with two different design philosophies, had to come together in perfect harmony while traveling at kilometers per second. You could compare it to connecting an Apple computer to a PC with an untested adapter. But here, a bad connection meant not data loss, but the crew being stranded in the vacuum of space. This also included the first crew transfer between the two vehicles. The astronauts had to pass safely from one spacecraft to another. And on top of all this, the crew was supposed to use the new Axiom Extravehicular Mobility Unit test, or AXEMU, spacesuits in the actual vacuum of space for the first time. Remember why the Apollo 9 mission was so critical. Apollo 9 didn't go to the Moon. It was a 10-day test flight in low Earth orbit where astronauts tested the lunar module for the first time, practicing docking and separation maneuvers. They did all this within a safety net where they could return to Earth in hours in an emergency. Because a failure on the Moon meant death. The original plan for Artemis 3, however, you eliminated this safety net. It was trying to perform not one, but at least 3 major firsts in a single mission, hundreds of thousands of kilometers from Earth. This is why the independent safety panel raised the alarm. The risks were not adding up. They were multiplying. Docking, refueling, suit deployment, and landing each had its own probability of failure, and when these probabilities were combined, the mission's chance of success plummeted. This was not prudent engineering. It was a gamble with human lives. NASA's cancellation of this plan was not a failure, but rather an acceptance of hard truths. It was a necessary step taken for the program's survival. But this decision was not just a postponement. It set off a domino effect that also changed the program's fundamental philosophy. This new philosophy led to the complete abandonment of one of the largest and most expensive parts at the heart of the rocket, and its replacement with a much different system. And this change determined the future of Artemis. And this change put the future of Artemis on a more modest, but far more achievable path, because the program's new leadership chose industrialization over romance, and repeatability over spectacle. This led to a fundamental change in the rocket itself. For years, the plan was to upgrade the Space Launch System, or SLS, to a more powerful version called Block 1B. This version featured a massive new upper stage called the Exploration Upper Stage, or EUS. But this upper stage became a cautionary tale in aerospace program management. It couldn't keep up with the program. Its costs soared, and it became a component that devoured huge budgets without ever reaching the launch pad. For this reason, of course, NASA, under the leadership of Administrator Jared Isaacman, cancelled the Exploration Upper Stage entirely. This was a decision akin to cancelling your order for a dream ultra-luxury sports car, and instead buying a reliable, not chassis, mass-produced sedan that you can take delivery of immediately, choosing what works. So, NASA chose a component that already existed and was already working. The Centaur 5 upper stage, produced by United Launch Alliance, or ULA. This was a dual-engine stage already in operational use on ULA's Vulcan rocket. It was flight-proven, it was in production, and most importantly, it was compatible with the existing Mobile Launcher 1, or ML1, at the Kennedy Space Center. This was a crucial decision, because it eliminated the need for Mobile Launcher 2, or ML2, a second launch platform being developed at enormous cost to support the larger Block 1B configuration. By standardizing the existing SLS design with the Centaur 5, NASA could continue to use the infrastructure it already had, reduce the gap between missions, and move towards a launch target of every 10 months. This was a solution that directly addressed the problem of skill atrophy. Because more frequent launches meant a sharper workforce, the logic behind this philosophy was industrial. A rocket that can theoretically lift more payload but never gets off the ground has no value. But a rocket that launches regularly, building institutional competence with each flight, has value. This was a move of pragmatism that saved the program's future. But the only technical change shaping the program's future wasn't the rocket itself. The hardware that would ensure the astronauts' survival was also undergoing a revolution, as especially the new generation of spacesuits, designed to counter what was perhaps the greatest threat they would face on the lunar surface. That threat wasn't radiation, it wasn't the vacuum, it wasn't the temperature, it was dust. Moon dust is unlike any dust you've encountered on Earth. It has never been eroded by water. It has never been rounded by wind. It has never been smoothed by biological activity. Each grain of lunar regolith is a microscopically jagged and angular piece of volcanic glass. Its edges are sharp enough to cut through seals and abrade optical coatings. The Apollo astronauts discovered this the hard way. After their moonwalks, they tracked lunar dust into the cabin of the lunar module. The dust coated every surface. It jammed equipment. Several astronauts reported respiratory irritation after inhaling it. Geologist Harrison Schmitt on Apollo 17 developed what he described as lunar hay fever. It manifested as hours of nasal congestion and sneezing. For a 3-day mission, this was manageable. But for a continuous presence lasting weeks or months, it was potentially lethal. For this reason, the new spacesuit, called the Axiom Extravehicular Mobility Unit, or AXEMU, was designed from the ground up to solve this problem. The Apollo suits, the A7L model Maxets, were engineering marvels for their time. But, by modern standards, they were comically restrictive. The suit is essentially a rigid balloon. Astronauts could barely bend their knees. They couldn't twist at the waist. That's why walking on the lunar surface required a hopping, hutch-house, bouncing gait, because the suit's joints didn't allow for a normal stride. And picking up a rock from the ground required a special tool, because bending at the waist was physically impossible in the pressurized suit. The AXEMU, however, Mockholtz, uses a hybrid structure. It combines hard-shell torso components with advanced fabric joints at the shoulders, elbows, hips, knees, las, and ankles. The result is a pressurized suit that allows astronauts to move with a range of motion never before achieved in space. They can walk naturally, they can bend over to collect samples, they can climb sloped terrain, and most importantly, the suit is equipped with seals and materials specially designed to resist the infiltration of lunar dust. The suit's life support system is designed to keep an astronaut alive in permanently shadowed regions for at least 2 hours. There, temperatures drop to negative 240 degrees Celsius. The suit features a visor system developed with Oakley, providing enhanced vision in the extreme contrast conditions of the lunar surface. Sunny areas are blindingly white, while shadows are impenetrably black. But perhaps most futuristic is the communication system, developed with Nokia. It provides a 4G LTE network between the astronauts, the lander, and orbiting assets. 4G on the Moon. This is a universe away from Apollo's thin bandwidth. Each of these technical leaps, more reliable rockets, more flexible suits, more robust systems, all serve the same purpose. Not just to go to the moon, but to stay there. But what's truly exciting is where these technologies will go and what they will make possible. Because the South Pole, the target for Artemis 4, is not just a landing site. It's a place where humanity can rewrite its destiny. And what they hope to find when they get there, and what they hope to find there, redefined the entire program. Not just a scientific curiosity, not just a geopolitical chess game. We are now accelerating to top speed, because this is the climax of the story. This is the real reason why, after half a century, humanity is going back despite cracked shields, leaking valves, and incredible costs. This is the story of why the future of not just a rocket, but our entire species, hangs by such a thin thread. Brace yourselves, because now, the real miracle begins. Full version called Block 1B. This version featured a massive new upper stage called the Exploration Upper Stage, or EUS. But this upper stage became a cautionary tale in aerospace program management. It couldn't keep up with the program. Its costs soared, and it became a component that devoured huge budgets without ever reaching the launch pad. For this reason, of course, NASA, under the leadership of Administrator Jared Isaacman, cancelled the Exploration upper stage entirely. This was a decision akin to cancelling your order for a dream, ultra-luxury sports car, and instead buying a reliable, not chassis, mass-produced sedan that you can take delivery of immediately, choosing what works. So, NASA chose a component that already existed and was already working. The Centaur 5 upper stage, produced by United Launch Alliance, or ULA. This was a dual-engine stage already in operational use on ULA's Vulcan rocket. It was flight-proven. It was in production. And most importantly, it was compatible with the existing Mobile Launcher 1, or ML1, at the Kennedy Space Center. This was a crucial decision, because it eliminated the need for Mobile Launcher 2, or ML2, a second launch platform being developed at enormous cost to support the larger Block 1B configuration. By standardizing the existing SLS design with the Centaur 5, NASA could continue to use the infrastructure it already had, reduce the gap between missions, and move towards a launch target of every 10 months. This was a solution that directly addressed the problem of skill atrophy. Because more frequent launches meant a sharper workforce, the logic behind this philosophy was industrial. A rocket that can theoretically lift more payload but never gets off the ground has no value. But a rocket that launches regularly, building institutional competence with each flight, has value. This was a move of pragmatism that saved the program's future. But the only technical change shaping the program's future wasn't the rocket itself. The hardware that would ensure the astronauts' survival was also undergoing a revolution, as especially the new generation of spacesuits, designed to counter what was perhaps the greatest threat they would face on the lunar surface. That threat wasn't radiation. It wasn't the vacuum. It wasn't the temperature. It was dust. Moon dust is unlike any dust you've encountered on Earth. It has never been eroded by water. It has never been rounded by wind. It has never been smoothed by biological activity. Each grain of lunar regolith is a microscopically jagged and angular piece of volcanic glass. Its edges are sharp enough to cut through seals and abrade optical coatings. The Apollo astronauts discovered this the hard way. After their moonwalks, they tracked lunar dust into the cabin of the lunar module. The dust coated every surface. It jammed equipment. Several astronauts reported respiratory irritation after inhaling it. Geologist Harrison Schmitt on Apollo 17 developed what he described as lunar hay fever. It manifested as hours of nasal congestion and sneezing. For a 3-day mission, this was manageable. But for a continuous presence lasting weeks or months, it was potentially lethal. For this reason, the new spacesuit, called the Axiom Extravehicular Mobility Unit, or AXEMU, was designed from the ground up to solve this problem. The Apollo suits, the A7L model Maxets, were engineering marvels for their time. But, by modern standards, they were comically restrictive. The suit is essentially a rigid balloon. Astronauts could barely bend their knees. They couldn't twist at the waist. That's why walking on the lunar surface required a hopping, hutch-house, bouncing gait, because the suit's joints didn't allow for a normal stride. And picking up a rock from the ground required a special tool, because bending at the waist was physically impossible in the pressurized suit. The AXEMU, however, Mockholtz, uses a hybrid structure. It combines hard-shell torso components with advanced fabric joints at the shoulders, elbows, hips, knees, las, and ankles. The result is a pressurized suit that allows astronauts to move with a range of motion never before achieved in space. They can walk naturally, they can bend over to collect samples, they can climb sloped terrain, and most importantly, the suit is equipped with seals and materials specially designed to resist the infiltration of lunar dust. The suit's life support system is designed to keep an astronaut alive in permanently shadowed regions for at least 2 hours. There, temperatures drop to -240 degrees Celsius. The suit features a visor system developed with Oakley, providing enhanced vision in the extreme contrast conditions of the lunar surface. sunny areas are blindingly white, while shadows are impenetrably black. But perhaps most futuristic is the communication system, developed with Nokia. It provides a 4G LTE network between the astronauts, the lander, and orbiting assets. 4G on the Moon. This is a universe away from Apollo's thin bandwidth. Each of these technical leaps, more reliable rockets, more flexible suits, more robust systems, all serve the same purpose. Not just to go to the Moon, but to stay there. But what's truly exciting is where these technologies will go and what they will make possible. Because the South Pole, the target for Artemis 4, is not just a landing site. It's a place where humanity can rewrite its destiny. And what they hope to find when they get there, and what they hope to find there, redefined the entire program. Not just a scientific curiosity, not just a geopolitical chess game. We are now accelerating to top speed, because this is the climax of the story. This is the real reason why, after half a century, humanity is going back despite cracked shields, leaking valves, and incredible costs. This is the story of why the future of not just a rocket, but our entire species, hangs by such a thin thread. Brace yourselves, because now the real miracle begins. And the first shocking moment, Hussey, came from the Moon itself. It wasn't a dead rock. It was a freezer that had been running for billions of years, and the treasure inside this freezer made the Moon's South Pole the most valuable real estate in the solar system. Water ice. But this was not a simple discovery. This was a revolution that changed everything, because the Apollo astronauts landed at the equator. This was a survival decision. It was the easiest, safest path. But Artemis 4, in early 2028, will not land at the equator. It will land at the Moon's South Pole. Why? Because the Moon's axial tilt is only 1.5 degrees. Earth's 23.4 degree tilt creates seasons. But the Moon's nearly upright stance creates permanent shadows at its poles. Craters that have not seen sunlight in billions of years. These are the coldest known places in the solar system. Temperatures drop to negative 240 degrees Celsius, colder than the surface of Pluto. This is a record-breaking cold. In this eternal darkness, water molecules carried by comet and asteroid impacts over billions of years have frozen and accumulated. The Moon was a water reservoir, and this water was only a 3-day space journey away. How could this be possible? This fundamentally demolished the economics of space exploration, because water could be converted into breathable oxygen and rocket fuel through electrolysis. The Moon was no longer a destination. It was a gas station, a launch point for missions to Mars and beyond. This was the moment the concept of in situ resource utilization, or ISRU, transformed from science fiction into engineering reality. We no longer had to launch every gram of fuel from Earth's deep gravity well. We could now use local resources. This was the difference between a camping trip and a settlement. This was the potential to break humanity's dependence on a single planet. The scientific community was shaken, because this turned the Moon from a passive museum into an active industrial hub. But the incredible prize offered by the South Pole also concealed its most terrifying threat, history's most insidious killer: dust, moon dust. This was not like the dust you know. It hadn't been rounded by wind for billions of years. It hadn't been eroded by water. Each grain was a microscopically sharp piece of volcanic glass, sharp enough to cut through seals, abrasive enough to wear down optical coatings. But that wasn't the real nightmare. The real nightmare was that this dust was also electrostatically charged by the solar wind. This gave it a sticky, almost magnetic quality. It clung to spacesuits. It infiltrated mechanical joints. Apollo astronaut Harrison Schmitt described it as lunar hay fever, hours of respiratory irritation. They reported that the dust smelled like spent gunpowder due to iron nanoparticles that oxidized when they came into contact with the humid environment of the cabin. For a short mission, this was a problem. But for a mission lasting months, it could be lethal, because long-term inhalation of these jagged glass particles could cause chronic lung damage similar to silicosis, which kills miners who inhale quartz dust on Earth. How could this be possible? How could it be that the greatest danger was not radiation or vacuum, but simple dust? This was a paradigm shift. It showed that establishing a permanent lunar base was about much more than just building structures. It meant a constant war, a war against an invisible enemy. This is why instruments like Duster, to be deployed on Artemis 4, were designed. These instruments would study how the dust behaves to help design future habitats, airlocks, and suits. The scientific community confronted the reality that the biggest obstacle to the dream of settling the moon might be the smallest particles. But the real earthquake wasn't happening on the surface of the moon, but on the political map of Earth. Because while NASA was rolling back its rocket to fix a helium valve, China was executing a lunar program with methodical and relentless precision. This was a race in the shadows, and China was winning. In 2020, China's Chang'e 5 mission landed on the moon, collected samples, and returned them to Earth, making China only the third country to do so after the United States and the Soviet Union. But this was just the beginning. In 2024, Chang'e 6 went even further. It landed on the far side of the moon. This was a historic first, a feat no other nation had accomplished. It collected samples from the South Pole Aitken Basin, one of the oldest and deepest impact structures in the solar system, and it returned them safely to Earth. Each mission built upon the last. Each mission demonstrated a specific capability. Each mission brought China closer to its publicly stated goal, a crewed lunar landing by 2030. How could this be possible? How could China's relentless progress be explained in contrast to NASA's decades-long pause? Because Beijing wasn't going to the moon for photo ops. They were racing for the same reason: the South Pole, the water ice, the resources, the strategic location. The first to establish infrastructure at the lunar South Pole would gain a practical monopoly over the most valuable real estate beyond Earth. The 1967 Outer Space Treaty states that no nation can claim sovereignty over a celestial body. But ownership and control are not the same thing. You don't need to own a mountain pass to control it. You just need to build a fortress on top of it. This was the space sector capture scenario, and Washington was terrified of it. And in the middle of this geopolitical chess game, the most fundamental, most primal fear underlying all this ambition and technology revealed itself: the fragility of our species. This was the ultimate climax of the entire program. Why are we going? Just to beat China? No, this was an insurance policy against the extinction of humankind. We are a single-planet civilization, every human who has ever lived, every work of art created, every scientific discovery made, every love story told, has existed on a single rock. A single asteroid impact large enough to reach the surface could end civilization in hours. A supervolcanic eruption from the Yellowstone caldera could plunge the planet into a volcanic winter for years. A pandemic more lethal and more contagious than anything we have faced could reduce the population to a fraction. A nuclear war between major powers could render the surface uninhabitable for decades. Any of these events is statistically plausible, and against all of them, we have the same vulnerability. We have no backup. There is no copy of human civilization. All our eggs are in one basket. All our files are on a single hard drive. Becoming a multiplanetary species is not a luxury. It is not a vanity project for billionaires. It is not an abstraction for science fiction enthusiasts. It is an insurance policy against extinction. And like all insurance, you buy it before the disaster, not after. The cost of building a permanent presence on the Moon and eventually Mars is measured in billions of dollars. But the cost of not doing so, if any of these existential risks come to pass, is measured in everything. Every future generation that will never exist. Every discovery that will never be made. Every child that will never be born. This is the weight that the Artemis program carries. It is not just a rocket program. It is the question of whether this species can take the first real step to survive. Water, dust, competition, and extinction. These four elements fueled the fire at the heart of Artemis. But, in the midst of all these massive forces, there were 4 humans inside a small capsule, and they, tomorrow, were going to go farther than anyone in human history had ever gone. And what awaited them there, in the absolute silence, was a reality greater than the moon itself, a cold, a ruthless, and an inescapable reality. Because this new era's space race was not just about rockets and engineering. It was a battle for the rules, the laws, postulates, and the alliances that would form the foundation of humanity's future civilization. We are accelerating. We are going to maximum now. Because this is not just the technical, quality, but the political and philosophical climax of the story. This is the moment that reveals the true motivations behind all that risk and cost. And the first epic moment exploded in the text of a treaty at a signing ceremony. But it triggered one of the greatest geopolitical earthquakes in history, the Artemis Accords. This was breaking a record. NASA brought together more than 40 nations around principles like peaceful exploration, transparency, and the use of resources. This was the largest multilateral alliance for space ever established in human history. A united front, a shared vision for humanity's future in space. But there was a dagger plunged right into the heart of this vision. 2 giant signatures were missing. China did not sign. Russia did not sign. How could this be possible? This was not just a diplomatic disagreement. This was a challenge. Because they announced their own alternative, the International Lunar Research Station. This was a program in direct competition with Artemis, with its own rules, its own partners, and its own architecture. The world was officially divided in space. 2 blocks, 2 visions, 2 rival power centers, competing to control the moon's south pole. the most valuable real estate in the solar system. This was a space sector capture scenario, and this scenario rendered the 1967 Outer Space Treaty meaningless, because that treaty said no one could own a celestial body. But you didn't need to own it to control it. To control a mountain pass, you just need to build a fortress on top of it, and China was moving forward with relentless speed to build that fortress. The scientific community was frozen, seeing the potential disaster of this division. This was the end of an era of cooperation and the beginning of an era of competition, and it came at a time when humanity needed unity the most. But this new war was not just between states. The second epic moment shone on the launch pad with the logos of private companies. This was happening for the first time in history. Artemis, unlike the entirely government-run Apollo, was based on a massive partnership with the private sector. This was a revolution. But it was also one of the biggest risks. SpaceX was building the lander. Blue Origin was providing an alternative lander. United Launch Alliance was producing the new upper stage. Axiom Space was making the suits. Nokia was providing the communications. This was the greatest constellation of private contractors in history. This was a new model for space exploration, a potentially more flexible and more cost-effective model. But it also created dependencies never seen before. This was a chain, and a chain is only as strong as its weakest link. If SpaceX's Starship refueling system wasn't ready, the landing would be delayed. If Blue Origin's lander fell behind schedule, the backup plan would evaporate. NASA's timeline was now only as fast as its slowest contractor. How could this be possible? Humanity's greatest adventure now depended not on the will of a single agency, but on the profit and loss calculations, production schedules, and competitive instincts of a series of different companies. This was the most epic, most risky marriage of capitalism and exploration. If it succeeded, it could accelerate humanity's expansion into space. But if it failed, it could drag the entire program into a swamp of commercial disputes and delays. The scientific community watched this new dynamic with concern. Because Apollo's success was the product of a single, focused will, the fate of Artemis or Kiswe was entrusted to the chaos of a market. And beneath all this geopolitical and economic chaos was the third and most fundamental epic moment that silenced all the noise, that put everything into perspective. Existence itself. Why are we bothering with all this? Why are we spending so much money? Taking so much risk? The answer lies in the simplest and most terrifying truth. Because we have no other choice. We are a single-planet civilization. Every human who has ever lived, every civilization, every dream, has existed on a single rock. This is putting all the eggs in one basket. It's saving all the files to a single hard drive with no backup. A single major asteroid impact. A single supervolcano eruption. A new and more deadly pandemic. A climate catastrophe spiraling out of control. Or a nuclear war. Any of these existential risks could end the human story abruptly and permanently. And against all of them, we have one common vulnerability. We have nowhere else to go. How could this be possible? How could a species that split the atom with its own intelligence, that can look back to the beginning of the universe, be trapped on its own planet? This is the ultimate meaning of Artemis. It is not a luxury. It is an insurance policy against extinction. The cost of establishing a permanent presence on the Moon, and eventually Mars, is measured in billions of dollars. But the cost of not doing so, if any of these risks materialize, is measured in everything. Every future generation that will never exist. Every discovery that will never be made. Every child that will never be born. For the scientific community, this was the most fundamental, most urgent argument. This wasn't just about exploring. This was about surviving. Finally, all these great powers and philosophies crystallized at a single point, in a single moment, the fourth and most personal epic moment, tomorrow. As those 4 astronauts circle around the far side of the moon, they will enter absolute radio silence for several minutes. All communication with Earth will be cut off. They will be completely isolated from every other human in existence. By 400,000 kilometers of empty space and the entire mass of the moon. This will be the deepest, most absolute loneliness in human history. 4 heartbeats in the silence of the universe. When they look out the window, they will see the view that only 24 people have seen with their own eyes. That moment is the one that will justify all the risks, all the politics, all the money. Because that moment is proof of why the human spirit is unstoppable. We wonder, we explore, we go to the edge of the unknown. Because that is who we are. These moments, a geopolitical division, an industrial revolution, an existential imperative, and a personal miracle. They all form the complex and contradictory soul of the Artemis program. But now, after this dizzying pace, it's time to stop and breathe. What do all these events ultimately mean for us as a species? Is this just the next technological step? Or is it something that changes the very definition of who we are as humanity? And at the end of this journey, what will we see when we look in the mirror? And now, after this dizzying pace, it is time to stop, to breathe, and to ask ourselves the most fundamental question. Amidst all this technology, this politics, this risk, and this ambition, who are we? In the silence of the moon's far side, what do we see in our own reflection? This journey is not just a rocket program, it is a mirror. And that mirror reflects back to us our deepest contradictions as a species, our most painful paradoxes. We now face the most important question. What does all of this say about us as a human civilization? Because this story is not just about going to space, it is about understanding ourselves. The first and most jarring paradox concerns our abilities. On one hand, we have the boundlessness of our imagination. We can dream of building cities on Mars, of traveling between the stars, of solving the secrets of the universe. On the other hand, we have our painfully slow and flawed ability to execute. In 1969, we managed to land humans on the moon with slide rules and computers millions of times weaker than today's smartphones. But now, with exponentially more technology, knowledge, and resources, we have spent more than half a century just to take a trip around the moon. How is this possible? How can we achieve less when we have so much more? The tragic truth of this contradiction lies in how fragile we are as a species. The gap between what we can imagine and what we can implement is far greater than we think. Forces like institutional amnesia, bureaucracy, political indecisiveness, and skill atrophy can drag even our brightest dreams into a swamp. We are learning the hard way how difficult it is to regain a capability once we have abandoned it. This is a sad truth, because it shows how much of our potential is wasted due to the obstacles we create for ourselves. But there is also a beautiful truth within this paradox, a truth that begins with but, because despite all these failures, delays, and disappointments, we keep trying. That cracked heat shield, that leaking valve, those postponed missions, they are not just symbols of failure, but also of a stubbornness that refuses to give up. Our dreams may always be bigger than our reality. But what pushes us forward is the desire to close that gap. Have you experienced this in your own life? Your dreams are also bigger than your current abilities. You have goals, but the path to them is filled with obstacles. But you too, strive every day to overcome those obstacles. This is what it means to be human, to reach for the impossible and fail, and then to reach again. The second paradox concerns knowledge, the nature and fragility of knowledge. On one hand, we have more data than at any time in human history. The blueprints for the Saturn V rocket still exist. All the telemetry data from the Apollo missions is stored in digital archives. All this information is at our fingertips. On the other hand, there is the fact that we have lost the ecosystem that built that rocket. The factories are closed, the suppliers are scattered, and most importantly, the quiet, undocumented knowledge that lived in the hands and minds of the people who did the work has vanished. How can we know less when we have more information? The tragic truth of this contradiction shows that knowledge is not just written text. Knowledge is a living thing. It exists through practice, through experience, through mastery passed down through generations. And when this muscle memory is lost, even the most detailed plans become blank pages. This is sad, because it shows how easily the wisdom of one generation can evaporate, if not passed on to the next. It is a loss as great as the burning of a library. But there is also hope in this paradox, a hope that begins with but, because lost knowledge can be rediscovered. And it may be harder, it may take longer. But human ingenuity is capable of resolving solved problems. Every technical challenge the Artemis program has faced is not just an obstacle, but also a learning opportunity. A new generation of engineers is relearning, the hard way, the lessons that the old generation forgot. And in the process, they are internalizing that knowledge even more strongly. You've seen this in your own life. You've had to relearn a skill you forgot. You've rediscovered knowledge you lost. Because knowledge is not static. It is a constant cycle of losing and regaining. And this cycle makes us more resilient. The third and perhaps most unsettling paradox concerns our motivations. On one hand, we have a noble, unifying cause like the survival of our species. The fragility of our planet and the risk of our extinction is an existential threat that should unite all of humanity for a single purpose. On the other hand, there is the fact that the strongest driving force for our return to the moon is a geopolitical competition with China. This is tribalism in its most primal form. We must get there before them. How is this possible? How can our greatest dreams be driven by our smallest, most divisive instincts? The tragic truth of this contradiction shows how thin the veneer of civilization is over our primal nature. Even in the face of the greatest threats that should unite us, we choose to compete with each other. This is sad, because while our common home is burning, we are still fighting over who gets the furniture inside. This is a potential self-destruct mechanism for our species. But even in this dark picture, a twisted beauty can be found. A beauty that begins with but, because sometimes, even the wrong reasons can lead to the right results. The Apollo program was not born out of a pure curiosity for lunar geology. It was a product of the Cold War. But the result was one of humanity's greatest achievements. Today, the race with China may be the catalyst that forces us to move forward on the path to becoming a multi-planetary species. Perhaps our species can only perform at its best when faced with a rival. Perhaps this competition is the fire that saves us from lethargy and pushes us to attempt the impossible. You too have noticed in your own life that sometimes you do your best work when you have a competitor. Sometimes the least noble motivations can produce the most noble results. So human nature is full of contradictions, and this contradiction is perhaps our greatest strength. And finally, beyond all these grand paradoxes, there is the most personal, most intimate one, the paradox of being there and being here. Right now, 4 people are floating in that void, hundreds of thousands of kilometers away from us, representing all of humanity, and the rest of us, 8 billion people, are here on this planet, watching their journey on screens. They are the tip of humanity's spear. We are the shaft of that spear. There are deeper meanings inherent in the nature of this paradox, this duality, and these meanings. And the meaning of this paradox reveals the simplest and most profound truth. We are a vicarious species. We conduct our explorations by entrusting them to the bravest few. The tragic truth of this situation is that we will never be able to fully feel the reality of that moment, the vertigo of the view from that window, the heartbeat in that absolute silence. We are only the ones who listen to the story, not the ones who live it. There will always be an insurmountable distance between us, the distance of a screen, a radio signal, 400,000 kilometers of empty space. This is a sad separation, because we can only witness the pinnacle of human experience indirectly. But at the same time, there is an indescribable beauty in this paradox, a beauty that begins with but, because those 4 people are not there just for themselves. They are there for us, for every single one of us. They are the living symbols of humanity's collective curiosity and courage. Their eyes are our eyes. Their steps will be our steps. Thanks to them, we are there too. You, listening to this voice right now, are actually a part of that mission, because your curiosity, your support, your very existence is one of the billions of people who make up the shaft of that spear. And a spear is not just its tip. Without its shaft, it has no power. Therefore, you are in that exploration. You are reaching into that void. You are a part of that moment. And this brings us to a final paradox about time itself, the paradox of rushing and waiting. On one hand, there is the ruthless indifference of the universe. The universe does not wait. Asteroids do not change their orbits. Solar systems do not remain stable forever. The risks of our extinction do not operate on our calendar. This gives us an urgent call to action. It sends the message, we must go now, because tomorrow may be too late. This is the purest form of our species' survival instinct. But, on the other hand, there is the agonizing slowness of space exploration. Designing and building a rocket takes decades. Political will comes and goes. Budgets are cut. A helium valve failure can set the program back by weeks. This reality, however, tells us we must be patient. It whispers that hasty decisions can cost the crew their lives, can destroy the entire program. How is this possible? How can we be forced to both rush and wait patiently at the same time? The tragic truth of this contradiction is the meaninglessness of our perception of time against the timescale of the universe. We, as creatures with average lifespans of 80 years, are trying to understand and cope with processes that span billions of years. And our haste comes from our own mortality. Our impatience comes from the desire to see the next step in our own lifetimes. But engineering and politics operate on timescales longer than a human life. This is sad because it reminds us of our limits and the forces beyond our control. But there is also a deep wisdom in this paradox, a wisdom that begins with but. Because this dilemma forces us to find the best solutions. Not just the fast one, but the right one. Not just the ambitious one, but the safe one. This is the art of constantly balancing ambition with prudence. The entire story of the Artemis program is the search for this balance. Every delay, every postponement, every change of plan is a reflection of the struggle between these two opposing forces. You too are searching for this balance in your life. On one hand, you want to reach your goals immediately, but on the other hand, you know you must be patient to take the right steps. This is the definition of maturity, and perhaps humanity, as a species, is just now reaching this maturity. After all these thoughts, at the end of the story, we are left with essentially one fundamental question, and this question is directed at you. It is a choice. On one hand, there is the uncomfortable reality of failure, a cracking shield, a leaking valve, a half-century-long pause. The picture of a species struggling with its self-created obstacles, wasting its potential. When you see this picture, it is very easy to feel a sense of disappointment, of cynicism. It's very natural to ask, why are we even bothering? To say, yes, it's not worth all this trouble. On the other hand, there is the stubborn, unshakable hope represented by those four people. In that small capsule floating in the void, the will to continue despite all failures, that unquenchable curiosity for the unknown, the desire to build a better future, a safer home. When you see this picture, it is just as possible to be filled with a sense of inspiration, pride, a feeling of possibility. Both feelings are valid, both are legitimate, because both are part of being human. We are the sum of both our failures and our dreams. But the question is, which one will you choose to nurture? Will you stay in the safe harbor of criticism? Or will you set out into the uncertain waters of taking a risk? We are now approaching the end of this journey, so we have come a long way. From dizzying speeds to moments of calm reflection, we know now that the story of returning to the moon is not just a story of technology. It is a complex dance between ambition and reality, knowledge and forgetfulness, noble goals and primal instincts, loneliness and togetherness, haste and patience. This is our story, in all its flaws and all its glory. Those old footprints on the lunar surface have been waiting, undisturbed for 54 years. As if the moon has been patiently waiting to see if we would keep a promise. Those 4 astronauts in the Orion capsule are taking the first step to fulfill that promise. They carry on our behalf the potential to add new footprints next to those old ones. And whether that potential will be realized depends on what we do next, because this journey, or cup, is really just beginning. And where it will take us. On this journey, we saw just how difficult it is to even go to our nearest neighbor, the moon. But What if I told you there are scientists searching for ways to break the ultimate speed limit of the universe, Marcet, the speed of light? Warp drives and wormholes are no longer just dreams. They are the theoretical blueprints for traversing impossible distances by bending the very fabric of space-time. On our next journey, we will unlock the secrets of traveling beyond the speed of light. Are you ready to bend reality?